Welcome everybody to our next video in our series on probability and statistics. I, as always, am Dr. Lathram, and today we will be talking about the binomial family of distributions. So let's begin with the notion of a binomial experiment. Now, a binomial experiment is something that's pretty simple on the surface, that it is consists of n identical trials, and each one of these trials will be independent. The possible outcomes for any particular trial are either success or failure. That's the only options that we have. The random variable that we're going to be interested in this particular situation will be the number of successes that you actually have in n trials. Now, kind of the last thing that we need to know about the probability of success on any single trial is going to be some value p, and p is going to be a real number in between 0 and 1. So that represents the probability of success on any particular trial. Now, just a little bit of notation that goes along with this. Usually we represent the probability of failure as just with the value of q being 1 minus p. So let's take a look at the case when n is equal to 2. So we have two particular trials. Well, we can represent the sample space as a tree, as we can see in the following picture. Now, because the trials are independent, the branching probabilities, so the probability that we apply to any particular node, are going to be the same for all nodes, because the probability of branching doesn't really depend on what particular value came before or where we are. And so branching from any particular value, we can just label with the value of P for a success and Q for a failure. So if we look at the branches now, and if we let y be our random variable that denotes our number of successes, we can see that the probability that we have no successes whatsoever corresponds to only one branch, where we have a probability of q for the first failure and a q for the second failure. So the probability that y is equal to 0 gives us q squared. The probability that we have one success, well, we can go down the branch where we have a success and then we have a failure, or we can have a failure and then we can have a success. Either way, we have a probability of pq for each particular path and two paths. So our probability that y is equal to 1 is 2 times p times q. And finally, for two successes, we have only one path where we have a success on the first trial and a success on the second trial, which gives us a value of p squared for the probability. If we now increase our number of trials with one more trial, so now we've got n taking on a value of 3, then again we can represent our sample space as a tree structure, and then looking at the paths through the tree, if we look at the probability that we have no successes whatsoever, that's going to give us a single path with just failure, failure, failure. So we have a probability of q times q times q, or q cubed. For y is equal to 1, we have one success, so we can either have a success and then two failures. We can have a failure, a success, and then another failure, or we can have a failure, and finally on a third time we get our success. So either way, the probability for one of those paths is going to be p times q squared, and we've got three paths that make up that particular condition. Likewise, for the probability of getting two successes, how can that happen? Well, we can have successes on the first two trials and a failure on the third. We can have a success, a failure, and another success. Or we can have a failure on the first trial and then successes the next two times. So either way, the probability of any particular path is going to be p squared times q, and we've got three paths for which that's going to be true. Finally, if we want three successes, then there's only one path that's going to do the job, and that's going to be p times p times p. And so we have p cubed for the probability of getting 3 successes. So now let's bump it up one more time just so that we get some examples going and we can really see what some of these patterns are, and maybe that'll help us whenever we're actually looking at the probability density function. So if we let n equal to 4, one more time, we've got a tree structure that's got 4 levels in it. And looking at now the probabilities for each one of those, again, we have only one path where we have no successes whatsoever, so the probability that y is equal to 0 is just going to be q times q times q times q times q, so we get q to the 4th power. The probability that we have only one success, well, we can have a success on the first trial and no other successes. We can have a success on the second trial and no other successes, a success on the third trial and no other successes, and a success on the last trial with no other successes. So we've got 4 possible ways that can happen, with a probability along any particular path being just p times q to the 3rd power. Bumping that up to y is equal to 2 now, so that we want 2 successes. Well, we've got 4 places, and we want 2 particular successes in there, so this is really going to give us a total of 6 possible paths that you can see outlined in the diagram up above, and the probability of any particular path is going to be p squared times q squared. So now hopefully you might be beginning to see a little bit of where the pattern is really emerging. If we got y is equal to 3 successes, then we can have a failure on the first trial, a failure on the second trial, a failure only on the third trial, and a failure only on the 4th trial. And that will give us a guaranteed 3 successes. And so the probability of that is going to be 4 times p cubed times q. And then finally, the probability of getting 4 successes on 4 trials is just going to be p times p times p times p, so p to the 4th power. Now, hopefully, those coefficients that were popping up there were starting to look a little bit familiar. If we think back a little bit, hopefully everybody has seen this somewhere in their mathematical career, but we've got Pascal's triangle. And Pascal's triangle, remember that we're generating the pattern. It's a triangular pattern. We've got 1s on the outside, and the value at any of the interior positions is going to be the sum of the values that are diagonally above it. And so 1 plus 1 is going to give us 2, 1 plus 2 is going to give us 3, 2 plus 1 is going to give us 3, a 3 plus 3 gives us 6, a 6 and 4 is going to give us a 10, and so on and so on and so on. Now, those things should look pretty familiar to us because we saw them also when we were talking about our binomial coefficients. And that's exactly what we need when we are developing our probability density function. So being a little more general, we suppose that we've got this experiment in which we're having k successes out of n possible trials. Now, on any particular path with k successes, we necessarily have to pass through the s node k times and the failure node n minus k times. So this means that the probability for any particular path with k successes and n minus k failures is going to give us p to the k times q to the n minus k. So that the number of paths, so now the question is how many paths are we going to have in our tree? Well, the number of paths is going to be equal to the number of ways that we can choose k positions out of n possible positions. And so that we are familiar with from our formulas from our counting formulas from way back, and that gives us the binomial coefficients of n choose k. So just to remind you what that formula is, n choose k is going to be n factorial over k factorial n minus k factorial. And so the probability that y is a particular value of k is going to be the binomial coefficient n choose k times p to the k q to the n minus k. Now, what that does is really let us not only define a single probability distribution, but we get a family of distributions. So if we have a positive integer n, and p is going to be some real number between 0 and 1, those are going to be our parameters, then a random variable y is said to have a binomial distribution with parameters n and p if and only if the PDF is a function from 0, 1, 2, 3 up to n into the real numbers, such that p of y is going to be n choose y times p to the y 1 minus p to the n minus y. And so the family of distributions, by the family we just mean a collection of distributions, and we've got determined, each particular distribution is determined by parameters n and p, and we'll denote the family of binomial distributions with a capital B and then the parameters n and p. So notation, what we see here is notation that we use to kind of the shorthand for saying that y has a binomial distribution with parameters n and p. So that'll be something that's maybe a little bit new to us, but we will characterize all of our families of distributions in exactly that way. So now kind of anytime anybody says that you have a probability distribution, you need kind of be thinking of, well, what are my axioms? Does it satisfy all of my axioms for probability? So first thing, are all of my probabilities non-negative? Well, in this case, p is a non-negative value. Q is a non-negative value because p is going to be in between 0 and 1. I know my binomial coefficients are all positive, so my probability density function is always going to be positive. Well, now what about the probability of my entire sample space? Well, for that, I turn to the binomial theorem to give me an answer. So the binomial theorem says that if I've got a positive integer, or 0, then if I've got x plus y to the n power, then I can express that in this summation form. And so what happens in my particular case, I have x is equal to p, y is equal to 1 minus p. And so when I plug those into the binomial theorem, I have 1 to the n power, which is just 1. And that is my summation. And so sure enough, my probability of my entire sample space is 1. That if I have two mutually exclusive subsets, then by nature of this being a discrete probability distribution, my third axiom is satisfied. And so yes, sure enough, my binomial distributions do satisfy our three axioms for probability distributions.